I got an email recently from somebody that I used to work with. They've been having problems with certain devices going down and then being able to source some sort of repair solution. So either the manufacturer or other repair companies they've let them down basically. So it's a case of either not being, well, making the excuse that they can't source the spares, or charging scandalous call-out fees. And by scandalous I mean tens of thousands of pounds just in a call-out fee. So what I've got here, it's an LVD laser safe press control safety system. Basically what this does is, on a large press brake machine, it monitors a laser which is fired across the sort of mating surfaces, and if you stick your hand in between the two into the blades, then it will stop the machine. That's the idea basically. And this is actually the second repair I've done on one of these types of devices. They've got two pretty much identical machines with two identical control systems. So let's take this thing apart and we'll see if we can diagnose what the problem is this time. So once the screws are off, we'll just prise the lid off, and that reveals all the gubbins inside. Okay, so inside we've got one sort of large I/O board and then a separate control board, communications. You've got some large chips in the center. They're all FPGAs, field programmable gate arrays. And then around the outside edge you've got these white opto-isolators and the main power sections. Across here you've got a load of serial inputs and outputs, all controlled with these FPGAs. If there's going to be any sort of a fault though, it's going to be on the outside of these opto-isolators, because that's what connects back to the rest of the main machine. So you can see it all along here, these are all opto-isolators. I'll go into a little bit more detail on those a little bit later, but basically they isolate what's going on in the middle from the outside world, so a fault on the machine won't sort of affect what's going on the inside. Just sort of lifting it there, and this board comes away. Okay, so a quick run through of what's underneath. We've got the main sort of motherboard underneath, some large microprocessor type devices, Coldfire MCF520s. I haven't looked up the data sheets for anything under here really, because I don't believe that anything under here is going to be at fault. These look like memory. They're in a sort of familiar package. Memory is often looks like that. It's in that kind of a package. That's STM28W800B, if you want to look it up. There's some other various logic devices and microcontrollers spread around the place. This looks like a row of, it'd probably be something like Schmidt triggers, just to provide clean logic out to the rest of the board. And then on the top there, a couple of large FPGAs, field programmable gate arrays, and then underneath it's all just power supply stuff. There's a couple of large coin cell batteries for probably a real-time clock, perhaps, I don't know. We've got a couple of oven-controlled crystals. They're fairly sort of schmick and special. I don't know why they'd need such a precise sort of time base. I don't know. So there you go, that's pretty much everything on the bottom of the board. Anyway, so what we've got is, we've got the connectors that connect out to the rest of the machine. These are all the various outputs out to the machine, and inputs as well. So what they do, what they're for, is they connect out to the rest of the machine and control all the various functions, motors, solenoids and all that sort of stuff. The next thing in line is these large solid state devices, and they're all referred to as high side drivers. So basically they're basically like huge transistors, or a switch if you want to view it that way. They're either on or off, they're logic level devices, they're not well, logic function devices. They're either on or off. They don't have any sort of linear capability. So there's power supply into these chips, and there's an input, that's the sort of signal in, that will tell the chip to turn its output on or off. And it also has a separate status line, which is separate from the output. And the status goes back out to a Schmidt trigger and can go out to various other places on the board. I haven't pinned the whole thing out, but I have done some testing and pinning it out just to make sure what it is that's going on. There's a bit of power supply up here on the left hand side. That's a linear regulator, and what I've discovered is that, you know, 24 volts comes in here, comes up to the regulator, and that powers everything around the outside edge. So there's actually no, it looks like all one board, but it's actually two boards, if in a way. If you look here, this nice neat row of components along here, and then a nice neat row of components along here, everything on the outside of these components is totally separate to everything that's on the inside. You can actually see that if you shine some light up from behind it. So we've got this I/O board, and you can actually see all the way along the top, you can see the light coming through where there's no copper. So there's no copper connecting the top of the board to the centre of the board. And that gap continues all the way around. And then all the way along the bottom there. And it's the same deal on the other side. You've got this gap all the way along. And the same thing right the way along there. So this is the other side of the same board. We've got the card connector that connects it to the rest of the motherboard. Here's all the opto isolators. Again, another row of opto isolators. Fairly decent sized driver circuitry. Will draw a decent amount of current, or source it or sink it, either way. And then on this side there's a ton of tiny little transistors. I haven't actually looked at which way round they are. I don't know if they're input or output. I imagine that they will be input. They'll be set up for something like common open collector, and then that way you can drive them into a certain state, and that will signal that something's happened to the rest of the board. And that's all there is really. You know, there's some bits and bobs, some microcontroller and processors and all sorts of other stuff, but all that's in the middle, and there's no electrical connection to this stuff in the middle out to the rest of the machine. So if something's happened out on the machine, it is very unlikely to get in here into the centre to all the processing stuff. All these opto-isolators won't allow that to happen. One of the things I've mentioned quite a few times is these opto-isolators. So what do? Okay, so basically an opto-isolator is an LED and then a light sensitive transistor, basically. So what you'd normally have is something a bit like that for an LED, and if you pass a current through the LED, it's going to light up. Nothing more complex than that. Within the same device, you've got a transistor. Now, the transistor doesn't have a base like a normal transistor does. It reacts to the light from the LED. So that is the complete opto-isolator, and what it's useful for is, say you've got, I don't know, a motor. You can connect a totally separate power supply up here to this motor, and then connect that to the ground of this separate power supply. And what happens is, across here, you pass a current through here, and that can be a totally separate system. The only thing that passes from this side across to here is light. So this system across here is not electrically connected to this system across here, but you can still sort of pass information. You can do things like pulse width modulate across here, and sort of pick that up across this side, so you can even, to a certain extent, pass semi-analog signals across. In reality, you wouldn't connect something like a motor or a large load up to an opto-isolator, because they can only, you know, normally do a few tens of milliamps of current. But that's the basic principle of what's going on. So on the laser controller, the way that that's working is all of the processing stuff is across here on the LED side, and all the processor sees is an LED. It lights up the LED, and light comes across, the transistor activates, if you like, and current can flow through here and switch something on. The way that they've done it is that they don't have a big load like this. What they'll have is, it'll be connected to a microcontroller, input, and the microcontroller will be looking at this line to get information about what's happening out on the machine. And there's probably going to be, I don't know, a 10k resistor or something like that, which just sort of pulls this line up to 10 volts. Normally this line would be at 10 volts because that resistor, well, I say 10 volts if your power supply is 10 volts. This resistor is pulling this line up to 10 volts, but because it's 10 kiloohms, it's not that much effort for the transistor in the opto-isolator to pull that low. And so when this LED lights, the transistor activates, and you've got a dead short here, and this line would then be pulled down to 0 volts, and the microcontroller can see the change from 10 to 0, and it knows that something happened out on the machine, even though it's a completely separate system to everything that's happening over here. So that's the idea of those opto-isolators. This is the test setup that I'm going to use. This is I've got the power supply up here, and then all the individual power drivers on the board. That's what this is. It's a VN750. We've got the front panel connector on the machine, and what I'm going to do basically is we've got a power supply comes down and feeds the power supply for the chip itself. It's a little bit more complex than that because it's going to go through the onboard voltage regulator, but you get the idea. So there's the supply for that chip, and then what I'm going to do is just use a 1K resistor to pull the input high. And what's going to happen is, well, what should happen is the output should go high and the status line goes logic low. That's the idea. That's what's supposed to happen. So what I should be able to do is inject power down here on the front panel connector. I should be able to pick up the output, and I'll have to probe for the status line to check each chip. Right, so this is the physical test setup. There's something I forgot to mention on this schematic, and that is that I've got a 10 watt 47 ohm power resistor here. So when I probe the output of these devices are actually working into a bit of a load. It's not much, but it's just to check that the output, it's not just a sort of floating voltage, it's able to drive that voltage into a load. So the way that I've got this set up is I've got my old Fluke 8840 monitoring the voltage across that resistor. So that will show the output of the power devices, these VN750s. And then separately I'm using this multimeter to check the status pin on each power device. So the first device is here, and the output across on the far multimeter, you can see that it's sitting at 0. And it can drive up to 9.8 volts. That's with a 10 volt supply. So the output of that device is working. The next one along is on this pin. Okay, there we go. So now we're getting our 10 volts there. Excellent. Next one, excellent. Excellent. And this last one is actually on here. Okay, there we go. Excellent, right. So the output's working on all of them. So now I need to check the status on each one. So now we're swapping over to the other multimeter. So it should be inverted. So it's high at the minute, and then it drives low, good. High at the minute, drives low, good. High at the minute, drives low. High at the minute, drives low, good. High at the minute, drives low. Okay, and there's our issue. The status pin on this device is dead. So this device we're going to have to swap out. This is the component that we've identified as being dead. It's got a status pin that isn't changing state when it's supposed to. So I've put some Kapton tape across the plastic front panel connectors just to keep the heat away from them. So what I'm going to do is going to heat this up, just throw some heat at it with the hot air gun, and then once we've put a bit of once we've raised the temperature of the board and the chip a little bit, I'm going to go in with my soldering iron and just wash out the solder that's in here with some 6040 tin flux, tin lead mix with built-in flux. It's, you know, regular multi-core stuff. And once we've got all that flushed out, we'll carry on heating it, and it should just lift straight off. The whole point of washing it out with some tin lead is that it'll lower the temperature, the melting temperature of the solder that's on the board, and we should be able to get it off fairly quickly that way. Okay, so here goes. I've got it set for about 350 degrees centigrade. Just get a bit more light in here. Okay. I'm just hitting the heat sink at the back at the minute. Ah. I'm going to hit it with tons of liquid flux here. There we go, and we're off. Now before it cools down too much, we're going to get rid of the old solder. We're getting there. There's not a lot can be done to speed this up really. This is a massive heatsink. It's directly tied into the ground plane for the rest of the board. So you need a pretty powerful soldering iron to be able to get away with doing that, because the soldering iron needs to heat up your solder braid, and it needs to heat up the solder, and it needs to heat up the ground plane above the melting point of the solder. Okay, so clean that up with a bit of acetone and a cotton wool bud. It's just to get all the old junk out of there. Okay, excellent. I'll just close that up, because what I'm going to do every single time is knock my tub of flux over. Okay, that's that all lightly tinned. Plenty of fresh flux. Here's a pack from the previous repair. These are susceptible to ESD events, so I've just been careful to these are susceptible to ESD events, so I've just been careful to touch the handle of my soldering iron before I got these out of the bag. The handle of my soldering iron has got a 10 meg resistor to mains earth, so it bleeds off any voltage standing on my body. We've just got to melt that solder. With any luck, this should be the repair complete now. So we're going to measure the output. The output there. There we go, excellent. So we got our 9 volts on there. So that's the output. Right, so that seems to have been a success. We've got the dead one out. I've just tested this off the board, and it's confirmed dead, so that was definitely in need of replacement. I've also been around all the outside edges. I've checked all the big output stages. These are all pretty similar, but they've got 2 inputs and 2 separate outputs. There's some here. These are sort of more like MOSFETs. Around all the outside edges there's loads of tiny little transistors around the edges. But to go through all of them would take a long time. I don't really think any of them are going to be dead. It's going to take less time to take this board and fit it back to the machine and try it out than it would take to go through all of these transistors. So for the sake of speeding things up, I'm just going to throw this back together, try and fit it to the machine, and we'll see what happens. If the machine fires up and it works just fine, then we know the repair was a total success. If it's still showing some sort of failure, then that confirms that obviously there's something else still wrong, and I'll come back here and put a bit more time and effort into these other outputs here. Okay, so I'll throw this back into the case. What I'll try and do is take some footage tomorrow when I'm at the factory of this being refitted, and we'll see if the machine bursts into life. Okay, thanks for watching.